Everyone. I'm going to give you a little bit of an overview of a paper that we published in October last year, but I'm going to try and build it up to sort of like motivate why we did this and why this is useful and what you might, as a quantum fluids community, be interested in as well. So to tell you a little bit about the objects that I'm generally interested in, neutron stars are one of the three types of compact remnants that we have out there that are formed at the end of stellar evolution. And neutron stars specifically are the remnants that are produced when massive stars that have something between 8 and 20 times the mass of our sun ran out of fuel and essentially collapse under their own gravitational attraction and explode in these massive supernova explosions that are some of the most energetic processes that we have in the universe. During these collapse processes, we have lots of electron capture processes that are essentially producing a lot of neutrons. So this is where the name neutron star is coming from. We have roughly 95% of the neutron star interior made up of neutrons, and additional to a few other particle species that I will mention in a bit. But so the object that we are interested in this case has something between 1.2 and 2.1 times the mass of our sun. They are roughly spherical structures that have radii between 9 and 15 kilometers. And if we look at the densities that this corresponds to, we find that their interiors can reach up to on the order of 10 to the 15 grams per cubic centimeter. On top of this, because the initial progenitor that forms the neutron star is also rotating, we have compact remnants that have relatively fast spin periods that can reach between 10 milliseconds and 10 seconds. And in addition, neutron stars also have incredibly strong magnetic fields that we think reach between 10 to the 8 to 10 to the 15 Gauss, which is, for comparison, the Earth's magnetic field is roughly half a Gauss. So it's many, many orders of magnitude larger than what we can produce even in experiments on Earth where we try and ramp up the magnetic field. So when we think about neutron stars interior, we sort of like are facing this challenge that we don't actually know what's going on very well. And that's because we don't really understand the nuclear equation of state of dense matter that is present in the neutron star interior. On the top right here, I'm showing you a sketch of the quantum chromodynamics phase diagram where we have the density on the x-axis and the temperature on the y-axis. And you can sort of see that this regime of low density and high temperature, which is what we can reproduce in collider experiments on Earth, isn't probing the same parameter space as neutron stars are. So in the case of the neutron star, we generally are in the low temperature, high density regime somewhere down here. This little line here marks roughly the saturation density, which is what we see in atomic nuclei on Earth. So we're really in the regime where we're above what we can produce in terrestrial situations. So we don't really know what's going on here. So we have some kind of like what I would call canonical understanding of what neutron stars actually look like in their interiors. Specifically, if I'm talking of what I would call a mature neutron star. So it's a neutron star that has roughly an age of 10 to the 4 years and has cooled down to temperatures on the order of 10 to the 6 to 10 to the 8 Kelvin. Just to give you an idea, 10 to the 8 Kelvin is roughly the keV range. So the structure for such a mature neutron star is illustrated with this cake slice here on the right-hand side. It's very much layered like you would expect from the Earth. So if we go from the outside to higher densities, we have a solid crust that's made up of a solid lattice, which is permeated by electrons as well as neutrons. And we have this outer core where we have a fluid of neutrons, protons, and electrons at sufficiently high densities, also muons. And then we have this inner core region here where we don't really know what's exactly going on, because that's specifically, I mean, as soon as we basically go into the blue regime, we're kind of extrapolating our understanding of the equation of state. And it's really difficult to actually say what's going on at these very high densities. However, for lots of like astrophysical application, a large scale like modeling of what these stars really do, we can very often decompose the star into a solid crust and a fluid core, which is also the picture that I'm going to return back to, I guess, in the second half of the talk. So although the neutron star that I just described, this mature object, is really hot in terms of like laboratory systems, they're actually very cold in terms of the extremely high densities that we have in their interior. And we can sort of get an idea that this is the case by looking actually at the Fermi temperatures of the neutrons and the protons, so the nucleons in our system, which is on the order of 10 to the 12 Kelvin. So if we specifically focus on the neutrons and the protons in this star, it's possible using sort of extensions of the BCS theory to actually calculate the critical temperatures or the energy gaps for the pairing of these nucleons into Cooper pairs. So on the right-hand side here, you see 3 sets of colors. The top is the energy gap and the bottom is the corresponding critical temperature as a function of density inside the neutron star. So this is specifically for the core. And you can sort of see that there's 3 different colors here because we think we have at least 3 superfluid components inside the neutron star interior. So one of these is the neutrons at the inner crust here that are pairing in a singlet state. There is the neutrons in the outer core that we have here, which are pairing in a triplet state, and the protons here are also pairing in a singlet state. And you can sort of see that there is some range of different gap models that people have predicted are correct or describing the system. And we don't really know exactly which one of these is the correct system. But if you think about this in terms of the actual critical temperature and a star having an ambient temperature on the order of like 10 to the 8 Kelvin, which is basically the x-axis down here, you see for most of these models, the outer layers, which would be the crust, which would be in this part of the plot, so the extensions here, you were well below these maxima of the critical temperature. So you definitely have like systems that are superfluid, and in the case of the proton, superconducting. So for a lot of like applications in astrophysics, if we want to model these systems, we can make this assumption that we have at least these 3 superfluid components. And from what I'm going to talk about for the remainder, I'm generally going to focus on the superfluid, so the non-charged systems, because the superconducting part is actually a bit that we understand even less. And that would be a different topic, I would suggest. But so there's also the possibility that we have even more superfluid or superconducting components here in the inner core. But generally for the purpose of what we want to try and model, making this assumption that we have at least 3 is a good start. All right, so I mentioned earlier that neutron stars are very fast rotators, and we have these superfluid components. So the question is, what is the impact of these superfluids in terms of what the star actually behaves or what we observe? And yeah, superfluids are these macroscopic quantum states that are characterized by a wave function that satisfies the Schrödinger equation. And if we use this information and define a superfluid velocity as the gradient of the phase of this wave function, we can essentially deduce that the vorticity is 0, so the superflow is irrotational, and superfluids in that case can't rotate like classical fluids. That's something that you all know very well, but we have to have these singular structures where the vortex or the superfluid flow rotates around this vortex-like structure. And each of these vortices carries a quantum of circulation kappa that's determined by natural constants, specifically in our system, the mass of the Cooper pair, which is 2 times the mass of the neutron, because I'm going to be focusing on the neutron superfluid. Now, in the simplest picture, we have everything being regular. These vortices form an array that on large scales, so if I look at it from far away, essentially mimic solid body rotation, so that I can define a surface area density of these vortices that's determined by kappa itself. And as I just said, C, the mass of the Cooper pair, is 2 times the mass of a neutron, so I can deduce this natural constant, and in that context, deduce this areal density of vortices for typical millisecond pulsar periods that you see here on the bottom left. So we have roughly 10 to the 5 vortices for a neutron star that rotates at 10 milliseconds per square centimeters. So if you extrapolate this to the entire neutron star, you have on the order of 10 to the 17 vortices. So that is a huge number of vortices that I have in my stellar interior that I want to understand. Now, you might ask, well, if I have that many, does it really matter? Does it really like impact any kind of like astrophysical observations in any sense? Or is it just like I look from far away and I just see the system rotate on a macroscopic scale, and these vortices have no impact. To get to that point where it does actually matter, I briefly want to have a quick interlude on how we actually observe neutron stars primarily. So I mentioned earlier that they are fast rotators with periods between 10 milliseconds and 10 seconds, and they have very strong magnetic fields. And you can see a sketch here on the right-hand side of what an idealized neutron star looks like. So it's this sort of dipolar field structure that has a magnetic axis that rotates around an axis, that's the rotation axis, that is actually very often misaligned. And because of this behavior, particles in the magnetosphere are strongly accelerated and produce photons, which we then sort of can observe as this radiation beam that's illustrated here as this sort of purple structure. And because of the fact that we have this radiation beam that rotates around the actual rotation axis, we see this very much like a lighthouse-like emission from neutron stars in the radio. So every time this radiation beam sweeps over our radio telescope, we see this blip, as it's illustrated here in this GIF. So we can observe these pulses. We call this timing, radio pulsar timing, very much like with a stop clock, but instead with a radio telescope. And we use that to really observe what's going on with neutron stars and how they rotate. And it turns out that they are incredibly stable rotators. For some of these millisecond pulsars, they have a higher stability than some of the atomic clocks that we have on Earth. So we can really use this feature of neutron stars to understand what's going on. And because of this like very regular behavior, we call them very often pulsars. So the whole like methodology is called radio pulsar timing. Now, if we do use this method to time radio pulsars, it turns out that the regular spin down of neutron stars, which is just a direct result of the fact that it's essentially a large magnetic dipole that radiates and loses energy. So it will slow down as a function of time, just a tiny bit if we actually observe this in real time, but it is possible to observe this with very accurate radio telescopes. We can sort of see that sometimes this regular spin down is interrupted by sudden hiccups that we call pulsar glitches. So there's a sketch of this here on the right-hand side. This is not to scale. These things are generally very tiny, so it's very much like a hiccup. It looks very much like the star is just like spinning up a tiny little bit during this glitch. But we can really understand what's happening in this process by looking at a little experiment. I like to show you these little videos of 2 eggs that are spun in both scenarios. So you see on the left-hand side, we use a finger to stop the egg and it will stop. So it will stop rotating. While on the right-hand side, the egg, once it's stopped, it will continue rotating again. And there's a key difference between these 2 eggs, which is the fact that the one on the left-hand side is cooked. So all the internal components are basically connected to each other. And if I stop the shell, I stop the entire egg. While on the right-hand side, if I stop the shell, the internal components of the egg white and the egg yolk continue to rotate. And once I remove my fingers, they can transfer angular momentum again to the crust and the eggshell. And I see the egg rotate again. So without really looking inside by this little experiment, I can basically figure out what the actual structure of the egg looks like. And this idea of having different internal components is really what's behind the actual glitch mechanism in the case of neutron stars. So these spin-out glitches can really naturally be explained in a very similar multi-component model as with our egg, where we had different internal components. And it turns out that the superfluid is really crucial to like building up this multi-component model, because it is possible, because of the interaction of these vortices with their environments, to really prevent the superfluid from spinning down. So I can do this essentially primarily, this is the standard picture that we do this in the neutron star crust, where the vortices can pin to the crustal lattice. And I can essentially like prevent the superfluid from changing its areal density, which is coupled to the angular velocity. And if I basically can't remove vortices from the system, I keep the internal superfluid in the crust at a constant angular velocity. While the remaining components spin down until something happens and this glitch is triggered, which is still a process that we don't fully understand. There's some ideas what's happening, but really like there is this coupling process at this point where the internal superfluid essentially acts as an angular momentum reservoir, transfers angular momentum, and then they talk to each other. And I see just the observational component that is linked to this pulsar motion or this pulsar lighthouse emission really spin up, and then they reach a new equilibrium. And depending on the pulsar, for some of these, we see this very regularly happen over and over and over again. So the key thing really is that the shape of this glitch really encodes a lot about what's hidden inside the star that we can't see, very much like for the egg. So the idea really is that we can use these imprints as very much like fingerprints of what's happening inside the neutron star. But to really do the inverse problem of using observations to describing and like making inferences on what's actually happening in the neutron star, we need very good theoretical models. And the problem is that in the case of the neutron star, to really like model this glitch phenomenon in its entirety, we really need to understand complex physics at 3 different scales. So there is this sort of like idea that we have individual vortices that were much like one tree, where we can try and understand how vortices, for example, interact with individual pinning sites or potentially with each other. So we have like a few individual vortices that we want to describe. We have on the order of like 100 vortices, maybe up to 1,000, where we have like a part of a forest. And then we have like this, like the dimensions where we have more than 10 to the 10 up to 10 to the 17 vortices. That we have this entire like neutron star rotate, and we want to model essentially what we observe. Depending on the 3 different scales, people have like tackled this problem in the neutron star community with very different methods. On the individual vortex side, so to model really individual vortices, this is something that in the lab context on terrestrial system, people would model with vortex filament models, which is something that hasn't really been done. But I know Julie Jacob Thomas at Newcastle is currently working on. So there is some room there to like look into the physics of the individual vortices that we haven't really done. So on the second sort of part of a forest kind of picture, we've had several people looking into this using GPE models, very much like in lab system. And Lisa spoke about this, I think, 2 webinars ago. So go and check out our talk if you want to learn a little bit more about this. And then we have this really like large scale picture, which is the one where the most work has been done in some sense, because the majority of the models that really look at this don't really use a fluid picture in the sense that they actually solve the hydro equations, but we can sort of generalize these to develop an effective essentially solid body picture where we can just solve this in 1 dimensions, where we just have a radial coordinate if we want any spatial dependence at all. So most of these papers, and there's many, many, many more, have looked at various aspects of this on a large scale setup. Apart from this first Peralta paper, there's like 2 more from 2006 and 2008 as well that looked at this in 3 dimensions, but in spherical shells. But this is really the scale that I'm going to focus on now for the rest of this talk, and really going to show you some of the results of what we produced in the paper that we wrote last year. So the numerical setup is illustrated here. So we really wanted to focus on this response of a 2-component fluid core to a glitch that is driven by a crustal superfluid. So I said earlier, the part that we think provides the angular momentum for the actual glitch in the very simplified picture is the crustal superfluid. So this is not the component that I'm going to model here, but I'm going to model essentially the response of the remaining star to this change in the crustal superfluid. So we've done this essentially by making the assumption that the neutron star crust is an infinitely thin boundary that you can see here, although it's not quite infinitely thin, but this is this gray bit. And we model the core essentially as a superfluid, which we denote by the index n. And then we have a viscous component that is composed of the protons and the electrons in this case. So we neglect muons, but we can basically just lump all these charged particles together and assume they interact on the scales that we are interested in as a single fluid component. Now, initially, we assume that everything is co-rotating, and then at some point, we essentially, by hand, change the boundary condition. So we change the rotation frequency of the normal component and just basically give it a tiny hiccup. So we're modeling this with an instantaneous change that or the size is given by this epsilon, which is on the order of 10 to the minus 3. This is quite a bit larger than the actual Newton star glitches that we observe, which are more on the order of like 10 to the minus 6 to 10 to the minus 9. But the actual physics is identical. If we ramp up the size of this, we just basically have reduced our computation time. So every single data point that I'm going to show you in a bit was determined on it took between a day and a week to produce each of the data points. So it would have been impossible to do this study with like a realistic value of epsilon. But the goal of the study was really to try and figure out what the cause response is to this instantaneous glitch for the full sphere for the first time. So this has never been done. So it had been done in a spherical shell a couple of years ago. But really like looking at the entire spherical structure is something that we did for the first time in this analysis. Okay, so the equations that we actually solved, you will be familiar with. Those are the HVBK equations that were developed for superfluid helium. And you see here, so we have an equation for the normal component denoted by N here and the superfluid component denoted by S. And we use the spectral solver or pseudospectral solver Daedalus to essentially solve these systems of differential equation, which is very straightforward. So our U's are the fluid velocities and rho are the densities. And we have a kinematic viscosity for the normal fluid system and additional chemical potentials that essentially contain all the different gradient terms that we usually have in these equations. These are also supplemented by an equation for the mutual friction force that is determined by the interactions of the vortices and their surroundings. And very much like in the lab system, it's determined by these two coefficients that are called B and B prime that are determined by the underlying mechanism that drives the interactions of the vortices. Before I show you some of the results, I'm going to show you some of the timescales that are relevant for the neutron star model and also explain some of the approximations that we had to make to actually be able to compute anything. So first of all, for like a realistic neutron star, the mutual friction timescale is on the order of 80 seconds for the mechanism that we think is the sort of like canonical or most dominant one, which is the scattering of electrons off of the neutron vortices. And typically the strength of this mechanism in dimensionless units for this B coefficient is on the order of 10 to the minus 2, and B prime is roughly 10 to the minus 8, so B squared. So that gives you something on the order of 80 seconds. While in the case of the Ekman timescale, which is the other relevant timescale for the problem, which is defined here, we have to figure out what's the dominant driver for the viscous mechanisms. And under the assumption that that's electron-electron scattering, would have an Ekman number that's on the order of 10 to the minus 9. So because of these two constraints that we have very small B coefficients and very small Ekman numbers, it was basically impossible to like solve this for like these realistic numbers. So we had to make some assumptions that were still allowing us to probe the range of physics involved, but also do this in a realistic computation time. So for the mutual friction coefficient, we varied parameters between order 1 and 10 to minus 3, and we just set B prime to half of the original B value. Doesn't really affect the results at all. It's not in there in the actual evolution at all. So we did check that. And that was also obvious from the form of the mutual friction force itself. And for the Ekman number, we used two different values. We used 5 times 10 to the minus 3 and 5 times 10 to the minus 4, just to sort of like see how much that actually affects the dynamics. Okay, so these are some of the results that we found. This is for an actual single component fluid, because we wanted to just sort of like check if we understand the dynamics for the single component system relatively well, and really understand if what we're seeing in the numerical simulations is what we would expect from our analytical understanding. So you can see here a time series of the spin up of the sphere, where red is basically the final spun up velocity, angular velocity in this case for the normal fluid. So what we see is that within roughly one rotation, we form this boundary layer, and then the rest of the fluid spins up on a timescale that's faster than just viscous diffusion as a result of what's called Ekman pumping. So the low angular velocity fluid is basically sucked into the boundary layer, spun up, and then sort of like recirculated back into interior. And you see that within like a relatively short amount of time, 16 1 over again our dimensionless units, you really spin up the full sphere like you would expect, also from like analytical calculations that you can do in cylindrical geometry. And it turns out if we look at the actual azimuthal velocity, we do really see that which is what we would expect from the Taylor-Perlman theorem, that the azimuthal velocity becomes axisymmetric, and we have these like constant magnitudes over cylindrical surfaces. So it becomes a very quickly a cylindrical problem, which is what we would expect. So this all works fine. So the actual numerical method and our implementation is correct in that case. The advantage of like having a numerical solver is that we can sort of look in the interior and actually figure out what the flow patterns look like. And in the case of a single fluid, this Ekman pumping leads to the formation of a stable circular flow pattern in the northern and the southern hemisphere. So this is what we would expect from the cylindrical problem, where we just have one basically across one side of the rotation axis. And the Coriolis force essentially splits this up into two. And that's what we see in this case as well. And to sort of like analyze the behavior as a function of the radial coordinate, we've made these like slices essentially as a function of different r's along the equator. So the blue ones are very close to the actual outer layer of the surface. So we're essentially taking snapshots in the boundary layer, and then we're moving further in with the different colors of red here. And this is just the spin-up behavior of the viscous fluid. And we've just denoted the Ekman time here. And you do see across the different layers, we essentially spin up the viscous fluid on the Ekman time, like we would expect. Okay, so how does this look like in a two-component fluid? So this is the similar picture as we just saw here in the single fluid system. But we have the normal component given in the same color again in orange, and the superfluid in green. And the top row is for a very weak mutual friction coefficient, and the bottom row is for a stronger mutual friction coefficient. And the actual patterns that we find are very similar in some sense to the results that Peralta et al. Found in their spherical shell, although they weren't particularly certain about the actual convergence of their solutions, and they had incredibly low resolutions. So this was like almost 20 years ago now. But yeah, there were like numerical limitations that weren't like making it clear if these were the actual like converged solutions. But we do see that our fluid solutions converge, and we do get very similar behaviors in some of these. So if we compare the top row with the bottom row, first of all, in the top row, which the weak coupling, we do really find that the fluids almost seem to move independently, which also makes sense because there is very weak mutual friction between those. So they sort of have the ability to develop independently. And in both cases, we see the formation of these circular flow patterns in the northern and southern hemisphere. While in the strong coupling regime, the superfluid sort of follows the viscous fluid pattern, and we do see that we don't actually end up with a singular cell in both of these, but we have a lot more small scale structures, which is something that we're currently looking into because that has potentially implications for other kinds of like astrophysical processes, because whenever we have like non-axisymmetric behavior, it might actually drive, for example, gravitational wave emission, and can actually lead to other effects that we might be able to use to probe the internal dynamics of the system. So we can also like look again at these snapshots that I showed you earlier to try and really understand if we can get an idea of what's really happening in the internal layers of the neutron star, or in our model neutron star, as a response to this glitch. So overall, the evolution is, if you look at the difference between the angular velocity, you do see it looks very similar. Just the time scales are very different. And we do again see this like cylindrical behavior as the system evolves. But the spin up of the superfluid is really delayed because of the fact that we have this mutual friction coupling. So in this picture, what we always have to do first, if we change the boundary condition, is we have to communicate the change in boundary condition to the normal fluid, which then builds up differential rotation with respect to the superfluid, and then mutual friction essentially kicks in and causes the superfluid to spin up as well. So because of this, we have this like delayed behavior, and it turns out that this mutual friction timescale that we typically assume is the relevant coupling timescale for the entire neutron star interior to really react to this change in the glitch really only works for the outermost layers because of this delayed spin up between the boundary condition and the actual normal component. So you can see here on the right hand side, this is the same plot again as earlier. The blue are the spin up curves for the boundary layer. But as the further we go in, the more difficult it is for the fluid to respond on the mutual friction timescale. So there's just a delay. And these in the little wiggles that you can see here, they are essentially due to the little flow patterns that you see here at smaller radii close to the origin. We did run one simulation where we just let the system evolve and they do disappear. So these are essentially just like little issues of the simulations themselves, but they're not like long-term artifacts that will stay around. So they do eventually disappear if you were to evolve this longer, which we didn't do for all of the systems because of computational limitations. So yeah, so in this picture, the superfluid in the outer regions is essentially spun up on the mutual friction timescale, but the further we go in, the longer it takes because of this delayed interaction. And we wanted to then figure out if we could characterize this delayed spin up in a more formal way. And what we did is we essentially used these curves for different values of the mutual friction coefficient. And we just fitted the functional form that you see here to the individual curves and extracted the spin up time for different, as a function of the Ekman number for different B's that you can see here on the x-axis. And what we see here is essentially how this like divergence from the mutual friction time is progressing as we move from the outer area, so from close to the surface of the sphere in towards the origin. So the diagonal line here, the solid line, is the actual mutual friction time scale. It fits the blue curves, the blue dots relatively well, and is the case for both of the Ekman numbers that we looked at. So once we sort of like go further in, you see that there is some divergence and these dots lie higher up in the system. Now, another thing that we notice is that there seems to be this sort of like break in the slope between these curves. So these seem to roughly have a similar slope, and these seem to have another slope. And this is actually something that people have found analytically from analytical considerations, although they weren't able to specifically determine what these slopes actually are, but people have suggested that there is this break, which sort of suggests that there is different mechanisms or different regimes for the coupling at hand. So to actually figure out if this is true in our data and simulations as well, we fitted a functional form for the spin-up timescale that has this form. So C, alpha, and the gamma here are free parameters that we fitted to our simulation results. And tau EK is just the Ekman timescale that we assumed depends on the radial difference from the surface of the star as we move inwards. And if we plot the actual measured spin-up timescale and divide it by this effective Ekman timescale, we see exactly that this behavior that roughly above 0.07, the Ekman, the timescale or the problem is characterized by 1/the square root of the mutual friction coefficient, while at the lower end, we don't really understand the behavior very well. And particularly in the case for the lower Ekman number, we do suspect that there is actually some viscous effects that start to play a role. But this is really the regime where we think that actually is relevant for neutron stars. And we don't see exactly the behavior that we expect for larger B. So there's definitely some space for us to investigate this problem further here. Now, I wanted to quickly go back to this picture where I introduced these 3 different length scale earlier and said that in principle, we kind of like need an understanding of what's happening at all different scales to model this larger scale that we eventually observe in the case of the neutron star, to really bring this all together. And I think this is really like trying to spread across these 3 different scales is really like where the low temperature community can really have an impact. And I just wanted to show you one of the examples that you probably heard of, but I still am always very excited about when I see this. But there was this experiment by Zagatse in the 1970s where they essentially, inspired actually by the long relaxation timescales that were observed after the first glitches in the 70s, they essentially built a very simple experiment where they tried to reproduce spin-up experiments in helium with different spheres, different temperatures, different pinning configurations, and so on. And their primary target wasn't to really produce glitches in these systems, but to really model like these long-term exponential timescales, which they did recover. But there's one figure in this 1980 paper of what they call a sudden acceleration in the system that they monitored as a function of time. And you do see that this is essentially the rotation rate of one of the cylinders in their experiment. And you do see it has this very characteristic spin up, which looks very reminiscent of the actual glitch that we see in the neutron star. So this is potentially the only accidental observed glitch in a lab system. And people in our community have tried to sort of fit the data from this plot by essentially reading off the points and see if they can get this to match with certain parameters of helium and so on. But the data quality is just very poor, and there's some errors in like descriptions of what the cylinder size or the sphere sizes are and so on. So it's very difficult to match this. But I think really this is like a region or an area where laboratory superfluids can really help us like model these small scale dynamics a bit better, because we just cannot dissect a neutron star, so we can't look inside. But we have all these tools and techniques to model lab systems, in this case helium. And I know that Rina Zeev at UC Davis is currently working on building a follow-up to this. So there is definitely a lot of like space to try and bring those different communities together to help us build better models of neutron star interiors. All right, and with that, I wanted to quickly conclude. So I hope I convinced you that studying the shape of pulsar glitches really provides a window into the neutron star interior, where very much like for the egg that we can otherwise not really access directly. And for the specific study that I showed you, we focused on the response of the spherical to component neutron star core following a glitch for the first time. And we found that the mutual friction timescale that we very often assume in our analytical models that are in 1D represents the superfluid spin up of the outer layers very well. But as soon as you go further inside, there's a lot of additional physics that are currently not accounted for. So there's extra stuff happening, which is something that we're missing at the moment. So things that we are currently looking at is improvements of the treatment of the crust. As well, I said earlier, we just had the crust as a boundary layer. But in principle, in Daedalus, you can stick on a second superfluid shell or fluid shell on the individual core. So we're going to try and see if we can actually model this like entire glitch process in a more realistic way and see what happens there. I also mentioned that we understand the outer layers relatively well, and specifically the high coupling regime. But for the low B values that are likely going to affect the neutron star interior, there's definitely something that we're currently missing. But that's also the regime where we're having a hard time of simulating something, just because it takes a lot longer to run these simulations. And another thing that is relevant in the case of neutron stars, not so much for the lab systems, but neutron stars are magnetized, I said this earlier. And also they have stratification. So we're trying to see how we can actually try and model this in a more realistic setup. And yes, the last thing that I wanted to point out, which is that, yeah, as I mentioned, there is a lot of room for us to like try and understand vortex dynamics on different scales better. And I think this is really where lab analogs can help us a lot to build better Newton star astrophysics models. Okay, thanks a lot.
Okay, thank you very much for this very interesting presentation. Do we have any questions from the audience? Gary Liu, please.
Hello, thank you, Vanessa, for a very nice talk. I do have a question. How do I understand the Ekman number to the lower, well, like in macroscopic physics, or how do we link that number to the laboratory experiments?
Yeah, so it's defined. Okay, it's essentially controlled by your viscosity here. So in some sense, I guess it's like the inverse of your Reynolds number. So like you can describe your system or like the relative contribution of your viscous terms with this Ekman number.
I see. Cool. Thank you. Now I'm clear now. Thank you.
Lev.
Thank you for a very interesting talk. What is observed, as I understood from your talk, what can be observed from this neutron stars is the magnetic field. Is there any connection to NMR on superfluid helium-3?
All right, so what you observe, okay, so let me go one step back. I might have not made that particularly clear. So what we observe is the rotation of the star. Okay, so we basically see these pulses, which we can link to a period. And because we have very accurate period measurements, we can measure a period derivative. Now, if we make the assumption that the Newton star is a rotating dipole, you can make an inference on what the magnetic field strength looks like if it is a dipole, right? So we have like an average understanding of what the macroscopic magnetic field does. We cannot really determine the internal magnetic field very well. We have like, this is like, measuring magnetic fields is a really, really difficult thing for Newton stars to do. Okay. So we don't really measure magnetic fields. Just I wanted to clarify this. Now, is there I don't think there is, because I mean, for your NMR measurements, I guess what you're seeing is sort of like an effective cross-section. And really like the Newton star magnetic fields that we measure with these kind of periods, they're like at an even higher level. I don't think you can compare those kind of like measurements in that case.
Again, thank you.
Well, while we wait for other questions, I was going to ask, I understand you didn't consider vortex spinning in the core in these simulations, but if we assume that there is some pinning there, what consequences will that have in the context of this delay that you described here?
Yeah, so good question. So I guess you can play with different scenarios for like how you model where have my HVBK equations gone? Sorry. How you model the different systems. So it will always be like an effective description of the system. So now I've made the assumption that my crust is the driver of this entire process. Okay. But what you could do in principle, you could write down an effective description of the system where the mutual friction force that I have here isn't the correct one. But you essentially like have some kind of like internal driver that gives you the initial differential rotation, and then you kick off the entire process afterwards. So you would have to have an average like macroscopic description of what that would correspond to in the picture that I have here. So this is like where I say you have to link the three different scales together in some sense. So I now have an effective prescription of the pinning in the crust by just making the assumption that it spins up the lattice, which then is the boundary condition essentially here. But so if you wanted to like include pinning, you would have to like, and to have that as a driver of your glitch, you would have to like modify your mutual friction force and your initial condition to represent that. But if you want to solve fluid equations, you always have to have a picture like this, where you now have to incorporate your small scale physics and how they affect the large scales, essentially. And you can come up with lots of different ways the different components interact with each other. And you can make your model, I guess, as complex as you want. But this was the first sort of like way to model what we think is happening in these systems.
Yes, I understand. Thank you. Before I give Dima a turn to ask a question, I will just remind anybody in the audience who is not in our mailing list that if you want to be added to the mailing list, then send me a message here or by email. Dima.
Yeah, thanks, Vanessa. I have a question about the analog system, the lab system, particularly helium-4. So what kind of angular velocity would be relevant to have a some sort of a comparison?
So I think the answer is you would probably not rotate them at the same rotation rate as the neutron star, because what you want to see is like the ideal scenario for like producing a glitch in a lab system. So you would probably be able to rotate them slower. So actually, have I got, yeah. So they didn't use lasers back then. If I understand this right, they had like a tiny reflective mirror on this, and they shone like a focused light beam from like a lamp onto this, and they measured that. So to be able to do that, you need a relatively weak, even at this system. So for these angular velocities, you needed a relatively low rotation frequency, I guess. Low. So you don't have like particularly like short periods for this system. I think it would like whenever you build something like this, you would have to actually do a calculation of what the mutual friction coefficients would be, and then extrapolate that to like the timescales that you would want to see, and what rotation rates that would are. But I think that's very much doable with like lab technology that we have at the moment.
All right, yeah, thanks.
Okay, Omar is next, please. Can you hear me? Just unmute yourself and ask your question.
You are unmuted. You should be able to hear you now.
Well, we can't hear you at the moment. Maybe if you write your question in a chat, I can read it.
Any other questions in the meantime?
I'm not seeing any other questions, so we'll have to wait for this one. I mean, I have some questions I can ask, but they are not so that important. So let's have this one first. Or well, maybe if it takes a moment. I was going to ask you. You said that superconductivity. Okay, here it is. So Omar's question is about the entrainment effect on all the Andreev-Bashkin effects. What would be the impact on the results shown?
I don't know exactly what the impact on the results would be, as we haven't solved that, but you would have to modify, we have to go back to our HVBK equations. So you would have some extra terms here that would include additional terms on the inertial side, and then you would have to basically resolve your differential equations. That's not necessary. So it's another thing that we didn't include. I should have probably mentioned this with magnetic field and stratification. That's another thing that you would have to resolve for to make it more realistic.
Thank you. Well, then I have a very kind of a general question, not so specific to this presentation, but you mentioned that superconductivity in a neutron star is understood even worse than superfluidity. What do we know about it then?
So I think this this entire like idea of having like macroscopic quantum condensates in the interior comes from like the sort of condensed matter side that started working on this, I'd say in the early 70s. And most of the considerations there are relatively like simple. I mean, there's a paper by Beinpethek and Pines that like literally like is 2 columns long that used to be sort of like the paper that everyone cited on the fact that there's a neutron star superconductor. And it really basically just like uses an argument of like calculating the Ginzburg-Lande parameter and just comparing what that would be, whether it's larger than the critical value or above that. And it sort of suggested that we essentially want to make, depending on where we are in the neutron star interior, so for the outer core that I showed you earlier, that was like dark blue, I think, and then the inner core, which is sort of light blue, that we have a type 2 superconductor in the outer layers and at some higher densities, depending on the equation that you use. But at some point, like a few times 10 to the 14, we switch to a type 1 superconductor. But the idea is really that flux expulsion in the neutron star interior takes a very long time, and you essentially cannot really expel flux from the neutron star interior. So you're stuck with the flux there. So you have a type 2 region or an intermediate type 1 region where you have macroscopic flux-free regions alternating with normal conducting regions. So that's sort of like the picture that people had for like a long time. And Toby and I, who's also in the audience, like had a bit of a look at like how we can calculate these corresponding Ginzburg-Lande parameters and the relevant critical fields for a system that's composed of a 2-component system. So we have actually superfluid neutrons and superconducting protons at the same time. And we sort of like still find that that's likely true for a large area inside the star. So that picture still holds, but we might have something where we have these kind of like type 1.5 superconducting regions where we have flux stuck inside the neutron star interior in macroscopic regions, but they have a specific separation in terms of the flux tubes. So that's something that we looked at a couple of years ago, but it's really difficult to like understand the full problem. Also in terms of like what's going on in terms of like a time dependent problem, because the neutron star cools through its transition temperature. So you have to kind of like factor in lots of these different aspects. And people have tried to model the neutron star magnetic field in terms of like superconducting pictures, typically by just assuming the flux is contained in the crust only and the core is in a Meissner state. So they essentially have a boundary condition that reflects a flux-free core. This is what most of the models that model neutron star magnetic fields have done for like a long time. So they have an effective prescription of a superconducting magnetic field that is just a boundary condition which says it's the flux-free system. But that's very unlikely to be realistic. So there's a lot of open problems in that kind of area and how we really model the magnetic field very well. Yeah, I think that's it. I mean, we also don't really know what the structure of the field looks like at birth. So we don't really know what the flux configuration really looks like before the star turns superconducting. So there's a lot of open problems there. And then we have different types of neutron stars. Some of them have stronger magnetic fields, others have weaker magnetic fields. So there's a lot of like open questions there that might give you different outcomes depending on the type of neutron star and the evolutionary history that you actually look at. And then, as you said, in principle, if you have something like flux tubes present, then they can affect your glitch. You're actually a superfluid, so they can talk to each other, which might be a way to probe them. But the models that we have for that at the moment, I don't think are sufficient to really do any kind of comparison with data really yet.
Oh, okay. Very interesting. Thank you. Well, we're approaching the full hour, so before many people may have to leave, I will say that The next webinar is likely going to be in February, but we will inform you when we know more details about that. And then before we close this, I have one more weird question I wanted to ask, which is, I think you mentioned that some neutron star rotation periods are really very stable, to the extent that they may be more stable than some atomic clock or whatever it was in detail.
Yeah.
Does it mean that we can use a neutron star as a clock? And has somebody done that?
So what people have done isn't necessarily as a clock, but there is some suggestions for a very futuristic scenario where we basically have to use intergalactic or galactic, I guess. Let's do galactic first. Space travel. And because these pulsars are very accurate clocks, in principle, if you have 3 of them, you can triangulate and can use the signal. If you were to have a tiny radio telescope, or if you do it in X-rays, you would have to have a tiny X-ray telescope on your space shuttle. You could use it as a GPS system. So the regularity of these, essentially, there's 2 systems or two projects that I know of that have made that kind of suggestion. One is, I think, Sextant on the NICE telescope, and then there's another one in Barcelona where I was at, where they're trying to sort of like play around with this idea. It's called Podium. So the idea that they are very stable, you need particularly millisecond pulsars, which are the very stable ones, and you can use them to really like triangulate your position in space on a very large scale very accurately, because we see them quite far. So if you were to use extragalactic pulsars, you could do that with extragalactic travel, but also in our own galaxy.
Okay, thank you. I'm not seeing any further questions from the audience, so I will thank the speaker for a very interesting presentation, and also the audience for a good conversation after it. And with that, I am going to close this webinar now. Thank you very much.
Thanks, everyone.